So let us solve this problem. So the transfer function of discrete time LTI system is given as the transfer function of discrete time LTI system is given as Hz is equals to 2 minus 3 by 4 z raised to the power minus 1 divided by 1 minus 3 by 4 z raised to the power minus 1 plus 1 by 8 z raised to the power minus 2. So this is the Z transform of discrete time LTI system. Now consider the following statement. Statements. The first statement S1, that is the first statement S1 is the system is stable. The system is stable and it is causal for ROC, that is modulus of Z is greater than 1 by 2. So the system is stable and causal for ROC modulus of Z greater than 1 by 2. Second is the system is stable and but not causal for ROC, that is modulus of Z less than 1 by 4. And third thing is the system is stable. The system is not stable and also it is neither not causal and it is not causal and not stable, and the ROC is 1 by 4 is less than modulus of Z less than 1 by 2. So S1 is stable and causal, ROC is given. S2 is stable and not causal, for ROC is modulus Z less than 1 by 4. And it is not stable, not causal, for ROC 1 by 4 is less than modulus Z less than 1 by 2. So these are conditions that is provided. Now we need to check that which one is correct. Which statement is correct. So we need to find out which statement is correct. So let us start the analysis. So Hz is given. So Hz is equals to 2 minus 3 by 4 z raised to the power minus 1 divided by 1 minus 3 by 4 z raised to the power minus 1 plus 1 by 8 z raised to the power minus 2. So this is Hz. Now we can write it in terms of this in terms of factored form, in terms of factors. So if we find out the factors, then we get 2z z minus 3 by 8. These are factors. So 2z z minus 3 by 8, then z minus 1 by 4 and z minus 1 by 2. So please check this relation. So it is 2z z minus 3 by 8 then divided by z minus 1 by 4 z minus 1 by 2. So let us discuss so what number of poles are there. So the poles are z is equals to 1 by 4 and z is equals to 1 by 2, and the zeros are z is equals to 3 by 8 and z is equals to 0. So z is equals to 0 and z is equals to 3 by 8 are the pole zeros, and these are poles. So z is equals to 1 by 4 and z is equals to 1 by 2 are poles. So poles and zeros are there. Now let us discuss that. So S1 is, let us discuss the first. So we have that ROC. The ROC is given modulus of Z greater than 1 by 2. So that ROC is given modulus of Z greater than 1 by 2. So let us discuss this first. So we have two poles. One pole is present at 1 by 4 and another pole is present at 1 by 2. So there are two poles that are present. One pole is present at 1 by 2 and another pole is present at 1 by 4. These are two poles. Now the first case S1, the ROC is given as modulus of Z greater than 1 by 2. So this is the ROC that is exterior to this circle. So the ROC is exterior to this circle. Modulus of Z is equals to 1 by 2. So the ROC is exterior to the circle. Modulus of Z is equals to 1 by 2. Now we can easily say that since the unit circle. So where is unit circle? So this is our unit circle. This is our unit circle of radius 1. So this is unit circle. So this is unit circle. Now since the ROC is containing the, so since the ROC is containing the unit circle, since the ROC is containing the unit circle, since the ROC is containing the unit circle, so the system is stable. So the system will be stable since the ROC is including the unit circle. So the system will be stable, and the system is causal also. The system is causal because the ROC is modulus of Z greater than 1 by 2, that is exterior to the outermost pole. So it is causal system also. So it is causal also. So we have a stable system as well as we have causal system. So it is stable and causal. So it is both stable and causal. So now let us discuss the second one, that is S2. Let us discuss the second system. So second system, the second system is that ROC is given as modulus of Z is 1 by 4. So we have one circle of 1 by 4, we have another circle of for 1 modulus of Z is equals to 2, and the unit circle is here we have unit circle. Here we have unit circle. So this is the unit circle. Now modulus of Z is less than 4. It means this is the ROC. So this is the reason of convergence. Now it is first thing is it is non-causal. It is non-causal. Second thing is it is unstable. Why it is unstable? It is unstable. Why it is unstable? Because the reason of convergence, the ROC does not include the unit circle. The ROC does not include the unit circle, so it is unstable. The ROC does not include the unit circle, so it is unstable, and also it is non-causal. So it is non-causal, it is unstable because the ROC does not include the unit circle. So this is that So this is our answer for system 2S2. So system S2 is non-causal and also it is unstable. It is non-causal and it is unstable. So let us discuss the third system. So third system is S3 and S3 is given that the ROC is between 1 by 4 is less than modulus of Z less than 1 by 2. So this is first circle of 1 by 2. This is second circle of 1 by 4. First circle of 1 by 4. Second circle of 1 by 2. Then we have that ROC is in between 1 by 4 and 1 by 2. So this is the ROC. Again we have this unit circle. Again we have this unit circle. So since that ROC, since the ROC does not include the unit circle, does not include the unit circle, so the system is unstable. So the system is unstable and also it is non-causal. Also it is non-causal system. Also it is non-causal system. So we have all this. We have covered all these conditions. So what we can say that S1 and S3 are true. So S1 and S3, so we have S1 and S3 that is true and S2 is false. S2 is false condition. So S2 is false condition and S1 and S3 are true conditions and S2 is false condition. Let us solve another problem. Let us solve another problem. A system with transfer function, a system with transfer function hz with impulse response hn is defined as h2 is equals to 1, h3 is equals to -1 and ehk is equals to 0 otherwise. So we have h2 that is equals to 1 and h3 is equals to -1 and hk is equals to 0 otherwise. So consider the following statement. Consider the following statement. S1, the statement S1 is hz is low pass filter and the statement S2 is hz is FIR filter, that is finite impulse response filter. Is low pass filter. So these are two statements. Now we need to find out which statement is correct. So let us plot that Hn with respect to n. So H2 is 1. So we have H2 that is 1. Then we have H3 that is equals to -1. So it is -1. And all other points are 0. So what we can say that surely this is a high pass, this is a FIR filter. So surely this is a FIR filter. So second thing is this is not low pass filter. This is not a low pass filter. This is not a low pass filter. These things are clear from this figure. These two things are clear from this figure. Now let us solve this problem. So xz is provided, the xz is given 0.50 divided by 1 minus 2z inverse, this is provided. So find the value of x0, and the ROC is given, that is ROC is less than 2. So we need to find out the value of x0. We need to find out the value of x0. Now we can write it as xn. We can write it, since it is a non-causal sequence, please understand that. So it is minus a raised to the power n minus u minus 1, that z transform is equals to 1 divided by 1 minus z inverse, and modulus z is less than modulus a. So this is the inverse z transform of this signal. Now what we are going to do here, that xn is nothing but it is equals to minus 2 raised to the power n u minus n minus 1. Now x0 is equals to 0. It is clearly it is showing that x0 is equals to 0. So this is our answer. So the problem is, a causal LTI system is described by the difference equation. A causal LTI system is described by the difference equation, and the equation is 2yn is equals to alpha y n minus 2 minus 2xn plus beta x n minus 1. Now the condition is, the system is stable if we need to find out the condition that the system is stable if the value of beta. So what are the conditions? So we have to write we have various conditions. So first condition is when alpha is equals to 2 and beta is less than 2. The second condition is we have alpha is greater than 2 and beta is also greater than 2. The third condition is modulus of alpha is less than 2 and infinite any value of beta. Last condition is beta is less than 2 and any value of alpha. These are conditions. Now let us solve this problem. So that's by taking the z transform on both sides of this equation, we take the z transform on both sides. So and also if we want to find out the impulse response, so that if this is a discrete time LTI system, then if we apply del n as input, then response we are getting is called basically the impulse response. The response we are getting is impulse response. So here what we are going to do, we are going to find out the impulse response. So step 1 is to find out the impulse response. So it is 2hn, that is equals to alpha h n minus 2 del n plus beta del n minus 1. So what we just written xn is equals to del n. So it is 2 hn alpha hn minus 2 minus 2 del n plus beta del n minus 1. Now we are taking the z transform on both sides. So taking Z transform on both sides, we obtain, taking the Z transform on both sides, we obtain 2hz is equals to alpha z raised to the power minus 2 hz minus 2 into 1 plus beta z raised to the power minus 1 into 1. Now what we are going to find out that hz is equals to 2 minus beta z raised to the power minus 1 divided by alpha z raised to the power minus 2 minus 2, and that is equals to 2z minus beta divided by z divided by alpha minus 2z square divided by z square, and it is equals to 2z minus beta divided by z into z square divided by alpha minus 2z square. So what we will get here, 2z minus beta multiplied by z divided by alpha minus 2z square. So this is hz. So this is hz. Now we can write further. We can write that since it is hz, so if we consider the stable system, then all the poles should lie inside the unit circle. So what we can do, we are going to find out the poles of this system. So it is 2z minus beta multiplied by z, and here we can get the poles. So to get the poles, we have to put 2z square minus alpha is equal to 0. So 2z square is equal to alpha. So z square is equal to alpha by 2. So z is equal to plus minus under root alpha by 2. So that modulus of z is equal to modulus of alpha by 2. So this is the pole. And for stability, if the system is stable, then modulus of z should be less than 1, means modulus of alpha by 2 should be less than 1, means alpha is less than 2. And it is for any value of beta, since it is independent, so it is for any value of beta. So the condition is modulus of alpha should be less than 2 for all values of beta. So the correct option is C. So the correct option is basically we have modulus of alpha is less than 2 and for all any value of beta. So the answer is correct is C. So C part is, we can see that what is C part. So we can say what is the C part, we can see here. So okay, it is 4. So the correct option is C. So alpha is less than 2 for any value of beta. Now let us do another problem. So the problem is the Z transform of signal is given as the Z transform of signal is given by Cz is equals to 1 divided by 4 z raised to the power minus 1 minus z raised to the power minus 4 divided by 1 minus z raised to the power minus 1 square, and its final value is we need to find the final value of this signal. So Cz is given, Cz is 1 divided by 4 z inverse 1 minus z raised to the power minus 4 divided by 1 minus z raised to the power minus 1 whole square. Now the final value is limit n tends to infinity xn is equals to limit z tends to 1, 1 minus z raised to the power minus 1 into cz into cz. So it is equals to limit z tends to 1, 1 minus z raised to the power minus 1 into 1 divided by 4 z raised to the power minus 1 into 1 minus z raised to the power minus 4 divided by 1 minus z raised to the power minus 1 square. So if we solve this, but we can find out that this final value is limit n tends to infinity xn is equals to we can solve this. The solution is 1 by 4 z raised to the power minus 1, then 1 plus z raised to the power minus 2, 1 plus z raised to the power minus 1, 1 minus z raised to the power minus 1, divide by 1 minus z raised to the power minus 1. So this cancel out, this will cancel out, and we are applying the limit here, limit z tends to 1. So applying the limit here will give us the value that is 1 by 4 into 1 into 2 into 2, so it is equals to 1. So the answer is, so the final value is 1. So the final value is 1. Let us solve another problem. So a linear discrete time system is given as a linear discrete time system is given as the equation z cube. This is the characteristic equation z cube minus 0.81 z is equals to 0. This is the characteristic equation. Now we need to do the find out stability of the system. So that characteristic equation is z cube minus 0.81 z is equals to 0. Then if we take z common, then it is z square minus 0.81 is equals to 0. Then z minus 0.90 and z plus 0.90 is equals to 0. So we have z is equals to 0, z is equals to minus 0.90, z is equals to 0.90. So what we are getting here, we have pole at 0, then we have 0.90 minus 0.90. So if we just see the stability of the system, then modulus of z is less than 1. Since the modulus of z is less than 1, so and also the all the poles are inside that, so what we can say that the system is stable, because that the modulus of z we have 90, it is 0.90. So all the poles are inside the unit circle. So basically all the poles are inside the unit circle, so system is stable. Since all the poles are inside the unit circle, so the system is stable. So the system is stable. Let us solve this problem. So we have input xk and it is applied. So it is applied to summer. So the diagram we are. So let us draw this diagram. So this is minus b, and there is a delay, that is z inverse, that is unit delay. Then we have scalar multiplier, and then we have summer, and this is output yk, and a part of output is fed back. So this is wk, and this is wk minus 1. Now we need to find out, so find out yz divided by xz. Find out yz divided by xz. So this xk is input, this is input, and yk is a response. So we need to find out that hz. We need to find out hz, that is yz divided by xz. So this is the transfer function. This is the transfer function. Now we have these are multipliers, and this is unit delay. This is unit delay. These are multipliers. This is unit delay. This is wk, and so let us solve this. So what we can see that this wk is equals to xk minus b times wk minus 1. So this is wk minus 1, this is wk. After applying that delay, we will get wk minus 1, then after multiplication with minus b. So taking that z transform, and also we have yk. Please understand that this yk is equals to wk and also wk plus a multiplied by wk minus 1. A multiplied by wk minus 1. So this is our equation 1 and this is our equation 2. So taking the z transform on both equations, so what we will get? So we will get wz, the z transform of wk is wz, and z transform of xk is xz, then minus bz inverse wz. And so we can just write wz terms together. So it is 1 plus bz inverse is equals to xz. So wz is equals to xz divided by 1 plus bz inverse. So this is wz. Now also yz is equals to wz plus az inverse wz. So yz is equals to 1 plus az inverse into xz divided by 1 plus bz inverse. So xz is equals to yz divided by xz, and that is equals to 1 plus az inverse divided by 1 plus bz inverse. So this is hz. So finally we are writing hz, that is equals to 1 plus az inverse divided by 1 plus bz inverse, that is equals to transfer function hz. So this is transfer function hz. This is transfer function hz. This is transfer function hz. Let us solve another problem. So the problem is the in figure 1 that is given below. In figure 1 given below. So what is figure 1? Let us draw the figure 1. So xn is applied to summer. Then Let us first draw this figure. So this is our figure, and we have this point. At this point, we have this is y1n. At this point, we have yn y1n, and let this is y3n. So and this is y2n. So let us solve this problem. So what we need to find out? We need to find out that find the expression of y1n and y2n in terms of xn. So we need to find out the expression of y1n and y2n in terms of xn. Second is find the transfer function y to z. Find out the transfer function y to z divided by xz in the z domain. So we need to find out the transfer function, that is y of this system, that is y to z divided by xz in z domain. And also we are assuming that all initial conditions are 0. It is given that all initial conditions are equal to 0. So it is given that the all initial conditions are equal to 0. So let us solve this problem. So it is easy to see that y2n is equals to xn minus 2yn minus 1 plus minus y1n minus 1. It is very easy to say that xn minus 2y1n minus y1. So it is y1n. Minus y1n minus 1, and also y1n is y2n minus 1. So what we will get here? We will get y1n is equals to xn minus 1 minus 2y1n minus 1 minus y1n minus 2. Now since y2n is y1n minus 1, so we will get y2n this is y2 and this is y1. So we get y2n is equals to xn minus 2 minus, this is 2 and this is 1, please correct. Then it is y2n is equals to xn minus 2 minus 2y1 n minus 3 minus y1 n this is n minus 2 and this is n minus 3. So this is y to n. This is y to n. Now we can see that if we take the z transform on both sides, then we will get y to z is equals to z raised to the power minus 2 into xz minus 2 z raised to the power minus 2 y1z minus z raised to the power minus 3 y1z. So this is y to z is equals to z raised to the power minus 2 xz minus 2 z raised to the power minus 2 y1z, then minus z raised to the power minus 3 y1z. Now we can combine these terms together, so we will get if we combine all these terms together, then what we will get, we will get y1z 1 plus, and using the relation that y to z is equals to z raised to the power minus 1 into y1z, we can use this relation also. Now we can use this relation in this means, so what is y1z? So y1z is y to z divided by z raised to the power minus 1. So we can use this relation, we can put the value of y1z here, so we will get all these terms will be in terms of y to z and xz. So finally what we will get, we will get y to z, please verify that, we will get y to z that is equals to z raised to the power minus 2 divided by z raised to the power minus 1 plus 1 whole square. Multiplied by xz. So what we will get here, let us write in next slide. So y to z we will get is equals to z raised to the power minus 2 divided by z raised to the power minus 2 divided by z raised to the power minus 1 plus 1 whole square. This is y to z. Now we can further write it as 1 divided by z plus 1 whole square. This is y to z. So y to z is basically and also multiplication of xz, and of course multiplication of xz. So y to z is what is xz? So xz is given, xn is given, xn is del n. So xz, it is given in question. So xz is equals to 1. So y to z is 1 divided by 1 plus z whole square into 1, and that solution is if we solve this problem, then the problem we can easily solve, and we can find out that the solution of this problem is yn is equals to minus 1 raised to the power n minus 1 u n minus 1 and multiplied by n minus 1. So it is better to write in this way. So it is minus of minus n minus 1 n minus 1 u n minus 1. Please check this, we have solved this type of question earlier also, so please check this. So this is our y to n, this is our y to n, this is our y to n. So let us solve. Okay, so let us start the Fourier analysis of continuous time signal and system. So the Z transform, we have seen that Z transform is applicable for discrete time LTI system. Now we are going to investigate the Fourier series analysis. We are going to do the Fourier series analysis of continuous time signal and system. So our heading is Fourier series Fourier series analysis of continuous time signal and systems. Fourier series analysis of continuous time signal and systems. So what is Fourier series? So Fourier series representation of periodic signals. So let us discuss the Fourier series. The Fourier series representation. Let us discuss the Fourier series representation of periodic signals. Let us discuss this first. The Fourier series representation of periodic signals. So first we need to know that what is periodic signal. I am again revising this concept. We have discussed this concept in a very first lecture. So a continuous time signal, xt is said to be periodic, A continuous time signal xt is said to be periodic if there is a positive non-zero value of t, if there is a positive non-zero value of t for which xt plus capital T is equals to xt for all values of t. So this is equation number 1. So this is the definition of periodic signal. So the fundamental period. So there is a fundamental period. So the fundamental period T naught of xt is the smallest positive unit, is the smallest positive unit or value of t is the smallest positive value of t for which equation 1 satisfies. And f naught is equals to 1 by t naught is called the fundamental frequency. So if we have yt is equals to sin t, then the fundamental is omega naught is 2 pi f naught, then f naught is basically 1 divided by t naught is equals to 1 divided by 2 pi. So the time period is 2 pi. So this is the minimum, this is minimum value of t naught. So sine 2 pi plus t is again equals to sine t. So the minimum value is t naught is equals to 2 pi. The minimum value is t naught is equals to 2 pi. This is the fundamental time period. So this is called the fundamental time period. So this is called the fundamental time period. This is called the fundamental time period. So two basic examples of periodic signals are the real sinusoidal signal, that is basically it is xt is equals to a cos omega naught t plus phi. So this is a type of signal that is called the sinusoidal signal. So this type of signal is called the sinusoidal signal. So this is one representation, and another representation is basically the complex representation. So we can also write it as a e raised to the power j omega naught t. So this is also the same plus phi. So this is basically the complex representation. This is the complex representation. This is complex representation of the sinusoidal signal, and this is simply sinusoidal representation. So next thing is we have complex. Let us start with complex exponential Fourier series representation. So let us start the complex exponential Fourier series representation. Fourier complex exponential Fourier series complex exponential Fourier series representation. Let us discuss this thing. So the complex exponential Fourier series representation of a periodic signal xt. So the complex exponential Fourier series the complex exponential Fourier series representation of a periodic signal xt with fundamental period t naught is given by xt is equals to summation k is equals to minus infinity to plus infinity ck e raised to the power jk omega naught t, where omega naught is 2 pi divided by t naught, where omega naught is equals to 2 pi divided by t naught. So where ck is known as the complex Fourier series coefficient, where ck is known as the complex Fourier series coefficients, complex Fourier series coefficients, and are given by, so these complex Fourier series coefficients are given by ck is equals to 1 divided by t naught xt e raised to the power minus jk omega naught t into dt. So let this is equation number 1. Equation number 2. So where this integral denotes the integral, so this denotes the integral over any one period. So it is integral over one period t naught, over one period, and 0 to t naught, or it may be from minus t naught by 2 to plus t naught by 2. So generally we are taking minus t naught by 2 to plus t naught by 2, and sometimes we are taking that integration from 0 to t naught also. Whatever we will find out the convenient, we are using this. So if we set k is equals to 0, so setting k is equals to 0 in equation 2, we obtain, setting k is equals to 0 in equation 2, we obtain what we are going to obtain. So we obtain c naught, that is equals to 1 divided by t naught xt dt. So which indicates that C naught equals the average value, C naught equals the average value, C naught equals the average value of xt over a period. C naught is equals to average value of xt over a period, where xt is real. So when xt is real valued signal, please understand that when xt is real valued signal, then c minus k will become ck conjugate, will become equals to ck conjugate. It is for real valued signal xt. So for real valued signal xt, that c minus k is equals to ck conjugate. So this c star indicates the complex conjugate. The star indicates the complex conjugate. The star indicates the complex conjugate. This star indicates the complex conjugate. So let us see the trigonometric Fourier series. So let us discuss the trigonometric Fourier series. So the signal xt is represented as xt is equals to a naught by 2 plus summation k is equals to 1 to infinity ak cos k omega naught t plus bk sin k omega naught t. So this is the representation of trigonometric Fourier series, and omega naught is equals to 2 pi divided by t naught, where ak and bk are the Fourier series coefficients, where ak and bk are the Fourier series coefficients. So ak is equals to 2 divided by t naught xt cos k omega naught t into dt, and bk is equals to 2 divided by t naught xt. It is integrated over the time interval t naught, so time period xt sin k omega naught t into dt. So this is ak and this is bk, and this is a naught divided by 2. So the relation between this AK and BK with CK is that C naught is equals to A naught divided by 2. This is the first relation. So we can prove that. So CK is equals to 1 divided by T naught, and it is equals to xt e raised to the power minus j 2 pi f naught k t dt. Now putting k is equals to 0, so what we will get here, we will get c0 is equals to 1 divided by t0 xt dt. Now we can see that it is nothing but a naught divided by 2, because a naught is equals to 2 divided by t naught, because a naught is equals to 2 divided by t naught xt dt. So C naught is equals to A naught divided by 2, because if we divide by 2 then it is equals to C naught. Similarly, we can find out the relation between AK with CK. So AK is equals to CK plus C of minus K, and the BK is equals to J times CK minus C of minus K. So this is the relation between AK and BK with CK, and so we can prove this also. We can prove this relation also, and also one of the important thing that is about C naught. So C naught is also called the average value. C naught is also called the average value or DC value. So C naught is also called the average value or DC value, because there is no frequency component in the measurement of C naught. If we just check that relation, that frequency, because we are considering K is equals to 0, so that is also called the CD zero value or DC value. Now we can also, a very important conclusion is that we can find out a very important conclusion. So the conclusion is that for a real signal, if the signal is real, so if xt is real, so the conclusion is that if xt is real, then ak is 2 times real part of ck, and bk is minus 2 times imaginary part of ck. So if xt is real signal, so this is for when xt is real. So when xt is real signal, then ak is equals to 2 times real part of ck, and bk is minus 2 times real part of ck. And also we can derive the relation between ck and ak and bk, and it is equals to ck is equals to ak minus jbk divided by 2. Please check this relation. So ck is equals to ak minus j times bk divided by 2. Similarly, c minus k is equals to ak plus j times bk divided by 2. Please check this relation also. So ck is equals to ak minus j bk divided by 2, and c minus k is equals to ak plus j bk divided by 2. So this is the relation. Now further we can see that if xt is even, then xt is written as a naught by 2. If xt is even, then bk is obviously equals to 0, so it is written as a naught by 2 plus summation k is equals to 1 to infinity ak cos k omega naught t. And if xt is odd, then ak is equals to 0 and xt is written as, and also we have a naught that is also is equals to 0, so we have xt that is equals to summation k is equals to 1 to infinity bk sin k omega naught t into dt. So when xt is even, bk is equals to 0, and when ext is odd, ak and a naught both 0, so we get xt only sine omega terms we will consider here when we have xt is odd, and only cos omega term we will consider when xt is even. So these are some important points that we need to consider for our Fourier series.